Section 4.7, the last section of chapter 4, is on antiderivatives. So if you think about addition and subtraction, multiplication and division, etc., they undo each other, right? Subtraction undoes addition. Division undoes multiplication. Well, it turns out there is an operator that undoes derivatives. And this is referred to as antiderivatives and also referred to as integrals. So why would we want to undo a derivative? Well, maybe we know the rate that something is occurring, so essentially it's derivative, but we want to know its position. That would be the original function. So in terms of the notation, the antiderivative of some function is often denoted using a capital f of x versus the question, which is lowercase f of x. Also, we mentioned integrals. They have this special notation, which is kind of like a long, skinny s in front of the function that we are taking the antiderivative of. And to verify the variable, we have a dx at the end of that question. Keep in mind, the derivative of an antiderivative gets you right back to the original function, right? If I had 2 plus 5, and then I subtract a 5, but then I add back a 5, I'm kind of back where I started if you followed all that. So if I started with some f of x and found its antiderivative to be capital F of x, well, when I take the derivative of that answer, I'm right back to where I started. I think this is a little bit more clear down below. So I have this lowercase f of x, which is x squared. I know the derivative is 2x. So if I want the antiderivative of 2x, that is, what function was this a derivative from? Well, it was a derivative of x squared. That's kind of how we started. But I can confirm this by taking the derivative of this answer. If I take f of x, which is x squared, and take the derivative, I get 2x. That is where I started in this realm. 2x has an antiderivative of x squared, whose derivative is 2x, where we started. But here's something super important. Wouldn't you agree that x squared plus 5 has a derivative of 2x because the plus 0 goes away? X squared minus a third has a derivative of 2x because the minus 1/3 becomes plus 0 when we take the derivative and it goes away. This means there could have been any constant when we find an antiderivative, and we don't necessarily know. Was it a plus 5? Was it a minus 1/3? So to be a little bit more generic, we just write plus c at the end. For example, look at all of these antiderivative rules, which we could figure out ourselves, but we'll go ahead and just start with a rule. If I'm asked to take the antiderivative, also referred to as the integral, of x to the n, for x being my variable, the antiderivative is to take that same base, to add 1 to the exponent, but because we know a derivative would put that out front, we need to multiply by the reciprocal of the derivative. You'll see examples in a moment, but we have this plus c to account for any generic case. And keep in mind, we've got this note over here. When it comes to a power rule, we do have a special case, but let's tie this back to what happened here. I had a function, well, actually, let's come down here. We had 2x. I thought of that as x to the 1. So I needed to add 1 to that to get my x squared, but I also needed to multiply by the reciprocal so that I just had x squared. Maybe that was too much for now. Let's just keep talking about the rules. Now, here is our generic power rule, antiderivative, but we said there's a special case. Remember, if the exponent is ever a minus 1, meaning our variable is in the denominator without a visible exponent, well, we know the derivative of the log is 1 over x, so this is a special case of the problem above, remembering that we can only take the log of positive, meaning non-negative, non-zero x's, we've got this absolute value just to kind of cover our case. And then we've got that plus c. So if I just had the integral of some sort of constant, like 5, then I would get 5x to be my answer. Well, plus some generic c. What if I had some constant or scalar multiple by a function? Well, just like when we take the derivative, we multiply by the scalar at the end, we can integrate and think of multiplying by that scalar at the end. When we take derivatives of two functions where we see them as added together, then we can integrate them as separate pieces. This kind of just happens naturally, that's some difference. Now notice this one. What if we have base e, we're taking the derivative of x, but x is in the exponent, specifically over the natural exponent. Notice we only say kx, even though we've taken more advanced derivatives. This is because we'll figure out those advanced ways when we do substitution. For now, we'll just say if it's e to the x and there's some sort of scalar, we will keep that, but we need to multiply by the reciprocal of the scalar. Now, if it was not base e and it's just any old exponential where x is the variable in the exponent, we need to remember that special derivative formula backwards where, we had a natural log of a. We know the derivative of the cosine is the sine, but it's negative the sine. Well, we're probably only integrating positive sine, so we need a negative here. When I take the derivative of this to check my answer, I would have the negative of negative sine of x, which is sine of x. So we can integrate the cosine. We can integrate secant squared because we tend to do sine, cosine, and tangent the most. But we also do secant occasionally. And don't forget those inverse trigonometric functions that we took derivatives of. That means we can integrate those derivatives to get back to our inverse tangent or trigonometric function.